In 1913, Bohr presented a model that led to equations such as Balmer's for the wavelengths that the hydrogen atom radiates. Bohr's theory begins with Rutherford's picture of an atom as a nucleus surrounded by electrons moving in circular orbits. In his theory, Bohr made a number of assumptions that combined the new quantum ideas of Planck and Einstein with the traditional description of a particle in uniform circular motion. Adopting Planck's idea of quantized energy levels, Bohr hypothesized that in a hydrogen atom, there can only be certain values of the total energy, electron kinetic energy plus potential energy. These allowed energy levels correspond to different orbits for the electron as it moves around the nucleus, the larger orbits being associated with larger total energies. Here we show two of the orbits. In addition, Bohr assumed that an electron in one of these orbits does not radiate electromagnetic waves. For this reason, the orbits are called stationary orbits or stationary states. Bohr recognized that radiationless orbits violated the laws of physics as they were then known. But the assumption of such orbits was necessary because traditional laws indicated that an electron radiates electromagnetic waves as it accelerates around a circular path, and the loss of the energy carried by the waves would lead to the collapse of the orbit. To incorporate Einstein's photon concept, Bohr theorized that a photon is emitted only when the electron changes orbits from a larger one with a higher energy to a smaller one with a lower energy. One might ask, how do electrons get into the higher energy orbits in the first place? They get there by picking up energy when atoms collide, which happens more often when a gas is heated, or by acquiring energy when a high voltage is applied to a gas, such as in a gas discharge tube like that in a neon sign. When an electron in an initial orbit with a larger energy, EI, changes to a final orbit with a smaller energy, EF, the emitted photon has an energy, EI minus EF, consistent with the law of conservation of energy. But according to Einstein, the energy of a photon is hf, where f is its frequency and h is Planck's constant. As a result, we find that EI minus EF equals hf. Since the frequency of an electromagnetic wave is related to the wavelength by f equals c divided by lambda, Bohr could use EI minus EF equals hf to determine the wavelengths radiated by the hydrogen atom. First, however, he had to derive expressions for the energies, EI and EF. For an electron of mass m and speed v in an orbit of radius r, as seen here, the total energy is the kinetic energy, Ke, of the electron, plus the electric potential energy, EPE. The kinetic energy is given by 1/2 mv squared. The potential energy is the product of the charge, negative E, on the electron, and the electron potential produced by the positive nuclear charge. In general, we assume that the nucleus contains Z protons, for a total nuclear charge of plus Ze. Later we will set Z equal to 1, since the hydrogen atom has only one proton in its nucleus. The electric potential at a distance r from a point charge of positive Ze is given as positive Kze divided by r. The electric potential energy is then negative E times positive Kze divided by r, and the total energy E of the atom is then given by E equals 1/2 mv squared minus Kze squared divided by r. We also know that a centripetal force of magnitude mv squared divided by r acts on a particle in uniform circular motion. This centripetal force is provided by the electrostatic force of attraction that the protons in the nucleus exert on the electron. According to Coulomb's law, the magnitude of the electrostatic force is equal to Kze squared divided by r squared. Therefore, mv squared divided by r equals Kze squared divided by r squared, or mv squared equals Kze squared divided by r. Substituting this into our equation for E and simplifying, we obtain E equals negative Kze squared divided by 2r. The total energy of the atom is negative because the negative electric potential energy is larger in magnitude than the positive kinetic energy. We still need a value for the radius r if this equation is to be useful. To determine r, Bohr made an assumption about the orbital angular momentum of the electron. The magnitude L of the angular momentum is given by the product of the linear momentum, mv, and the radius r. Bohr conjectured that the angular momentum can assume only certain discrete values. In other words, L is quantized. He postulated that the allowed values are integer multiples of Planck's constant divided by 2 pi, or L sub n equals mvn Rn, which equals nh divided by 2 pi, where n equals 1, 2, 3, etc., and h is Planck's constant. Solving this for Vn, we get Vn equals nh divided by 2 pi m times Rn. Substituting this into our previous expression and solving for Rn, we obtain Rn equals h squared divided by 4 pi squared mke squared times n squared divided by z, which is the radius of the nth Bohr orbit. If we plug in the values for all of the constants, we have Rn equals 5.29 times 10 to the negative 11th meters times n squared divided by z. Plugging this into our previous expression for the energy, we obtain En equals negative 2.18 times 10 to the minus 18 joules times z squared divided by n squared, or this is also equal to negative 13.6 electron volts times z squared divided by n squared. The number of protons, z, equals 1 for hydrogen, and the ground state radius, the smallest possible radius, is given when n equals 1. Plugging in the values, we have R1 equals 5.29 times 10 to the negative 11th meters. This is called the Bohr radius. The corresponding ground state energy is negative 13.6 electron volts. It is useful to represent the energy values given by this equation on an energy level diagram as shown here. In this diagram, which applies to the hydrogen atom where z equals 1, the lowest energy level is called the ground state, to distinguish it from the higher levels which are called excited states. Observe how the energies of the excited states come closer and closer together as n increases. The highest energy level corresponds to n equals infinity and has an energy equal to 0. This is the energy of the atom when the electron is completely removed from the nucleus and is at rest. In contrast, the lowest energy level corresponds to n equal 1 and has a value of negative 13.6 electron volts. The electron in a hydrogen atom at room temperature spends most of its time in the ground state. To raise the electron from the ground state to the highest possible excited state, 13.6 electron volts of energy must be supplied. Supplying this amount of energy removes the electron from the atom, producing the positive hydrogen ion H+. This is the minimum energy needed to remove the electron and is called the ionization energy. Thus, the Bohr model predicts that the ionization energy of atomic hydrogen is 13.6 electron volts, in excellent agreement with the experimental value. To predict the wavelengths in the line spectrum of the hydrogen atom, Bohr combined his ideas about atoms with Einstein's idea of the photon. As applied by Bohr, the photon concept is inherent in the equation EI minus EF equals HF, which states that the frequency f of a photon is proportional to the difference between the two energy levels of the hydrogen atom. This can be related to the wavelength lambda by noting that f is equal to c divided by lambda. Substituting our equation for the total energies, EI and EF, into this equation, we obtain the following expression for the emission lines. With z equal 1 and nf equal 1, this equation predicts the values for the Lyman series. Thus, Bohr's model shows that the Lyman series of lines occurs when electrons make transitions from higher energy levels with Ni equal to 2 and higher to the first energy level where Nf equals 1. Notice that when an electron makes a transition from Ni equal 2 to Nf equal 1, the longest wavelength photon in the Lyman series is emitted since the energy change is the smallest possible. When an electron makes a transition from the highest level, where Ni equals infinity, to the lowest level, where Nf equals 1, the shortest wavelength is emitted since the energy change is the largest possible. Since the higher energy levels are increasingly close together, the lines in the series become more and more crowded toward the short wavelength limit. The energy level transitions for the Balmer series occur when Ni is equal to 3 and higher and Nf equals 2. These emitted wavelengths are in the visible part of the spectrum, and we can see them with an optical grating spectroscope. The optical emission lines are shown here.